Hello everyone, welcome to another little lesson. I will cover a few facts today, mainly going over resistance and Ohm's Law, some things that are very vital to our understanding of electrodynamics. So let's jump right into it. Okay, so let me give you the equation that you should have seen before, and this is going to be R equals, and we call this rho, okay? It's like a P, but it's a little different. So R equals rho times length over area. So this is the equation to find resistance. And I will kind of try to go over what every single part means and what it relates to in an actual wire and an analogy. So first, R represents resistance. So that is, when you think of resistance, what do you think of? A revolution, right? Okay, maybe not that. Maybe Star Wars a little bit. But in this situation, it's the actual resistance, properly named, of the current. Think of it as an electrical inertia, which I will refer to actually later. So the resistance is properly named, simply meaning just the slow of the flow of charge through a circuit. This rho that looks like a funky P is actually called resistivity, which refers actually to the resistance of an object. So this is the length of the wire, and this is the area of the wire. So you all know I am a phenomenal artist. This is a beautiful cylinder. Okay. Now, we should know what the length is. The length of the cylinder would be from here to here. You could think of it as the height, but I will refer to it as the length. So imagine a wire or any kind of tube where anything flows through. The actual length, that is what it refers to. Now, is everything shaped like this? Of course not perfect. Nothing's perfect, except for this drawing, of course. And then the area refers to the area right here. Essentially the base. Now, resistivity. This is, resistivity is something that is part of a material which allows the electrons to flow. So imagine I had something like copper or rubber. The resistivity of both of those is quite different. Something like rubber would not allow electrons to flow very freely. It's just the way that is. Same thing with copper. The way that it is arranged in its solid state allows electrons to flow very freely. Same thing with gold and silver. Now let me get back to the analogy that I wanted to reference earlier. Most people use this as similar to rocks or a dam along some kind of river or waterfall, which is a great analogy. I love it because I love nature. However, I think one that may hit closer to home is something like traffic. And this is not a perfect analogy because roads specifically are not three-dimensional. I mean, they are, but not in the sense where it's like some tube. You're just kind of flat on the ground. But I still think the idea works well. So think of you trying to go to on some road trip somewhere that you love, or maybe to get some ice cream, anywhere you want to go. Think of the length as the actual distance between where you start from and where you end. Think of the area, as the number of lanes or the type of, or actually the number of lanes would be best. So the further you are, the longer the trip is going to take, right? Also, the more lanes you are, the more lanes that you have, the more opportunity you have to not be stuck in traffic. Okay, so the more lanes, imagine if you had one lane and you had a semi right in front, that might take some time. And now the resistivity could be the number of cars or the speed limit on the particular road that you're on. So if you're on a one-lane road near a school, the resistivity could be the speed limit. where you could go 25. Or if you're on a freeway, the resistivity could be quote-unquote less. It would be the opposite. So think of the speed limit as being the opposite of resistivity. So the bigger the speed limit, the more this goes down. So, if you have to travel by freeway somewhere, even though it might be longer, because there are more lanes and because the speed limit is higher, the resistivity goes down, so the resistance would be low as compared to you trying to get somewhere at 8 o'clock in the morning near a school where there's lots of buses and kids moving around. You're going to have a tough time moving around safely. So hopefully that analogy works well for you. I will keep using that because I think it works pretty well. It creates a good job, a good image in your mind to relate to. If not, maybe you can think of some yourself and get back to me, or ask me and I'll try my best to find something else to help you out. Now, this is the moment, even though you may not have realized it or don't know, this is the moment that we have all been waiting for. If equations were knees, this equation would be that of bees, a bees equation, or the bees knees, as you will. This is as important as those that you have heard before. You ever heard of E equals mc squared? I think so. You know Newton's second law, which is, of course, F equals ma. This is on par. It is at that level, at that echelon, that S tier. V equals I times R. Now, what in the world does that mean? Remember that voltage, okay, or electric potential difference, more like. So if I say voltage or potential difference, know that this is what I'm referring to. I, if you will remember, refers to current that is measured in amperes. I know. Also, resistance is measured in ohms. One thing besides the usefulness of this equation and the simplicity is that volts is named after Volta, an Italian scientist. Long story, but it was named after Ampere, a French scientist, and R is named after Ohm, a German scientist. So this is, a mixture of many people coming together from different locations at different times, and all of this just kind of falls into place. So I will bring, because I like analogies so much, I will bring an equation that we know so well that I just referenced, Newton's second law, which is, of course, F equals ma. However, I will write it in a slightly different way. F equals A times M. Now, voltage or electric potential is technically not a force. However, later on you will find that it can be referenced as electromotive force, which is something a little different than the voltage of a circuit. EMF is also the reference. So voltage, potential difference, or EMF. I know, many things to keep track of. But EMF is an ideal battery, kind of like an ideal gas, or assuming something falls with no air resistance, that's what that would stand for. But, as we know, there's no such thing as an ideal anything. Those are just fantasies that we make to make physics learning easy and fun. So, back to these equations. Now I have F equals AM in this situation. I'm going to compare these two. Again, they're not, voltage is not a force, even though it may be referenced later. Remember what force is the amount of push or pull or something. And voltage can actually behave in a similar way. It's how much the charge wants to move within the circuit. Now, M refers to mass, which is also the inertia of that system. So that if I have a force, imagine a gravitational force, the acceleration This would be constant, but this would be dependent on how much mass you have. Now, let's look at this situation. The current of the circuit will be dependent on, well, of course, the voltage of this system, this circuit. So if you have one battery, we assume the difference in potential will stay the same. So if this stays the same, then the current is completely dependent on, well, what type of battery you have and also the resistance within the circuit. And again, some of you might think, like, why is it important that we have resistance in general? Why can't we just let the electrons flow freely? Well, just think of some of the components in your computer. If you just let the same current run through all of them, maybe some components might blow up. They can't handle that much current running through them. So this really allows us, we can play around with that and allow us to kind of change how the voltage and current interacts with the whole system. So this is actually quite useful, even though you might think of it as a bad thing. Resistance is not a bad thing. So again, I like to think of resistance as an electrical inertia. This will help drive, help control how much current flows through my system. And this is the initial driving force that allows a charge to move through the system. And of course, delta V is measured in volts. I, the current, is measured in amperes, and R, resistance, is measured in ohms, which, even though it has the name resistance, it is the most tranquil of all of the measurements that we have. Ba-dum-bum. Now let us remember that how things are connected. So current is directly proportional to voltage, and resistance is, you can think of it as the same way, but not exactly. They're actually kind of independent of each other. But these two are inversely proportional. So one of the questions that I asked you is, which of the following will cause the current through an electric circuit to decrease? So what would make this go down? Well, let's think of two things. To make this go down, either the voltage has to go down or the resistance has to go up. One of those situations has to happen. They both can happen, which would actually cause that to happen as well. But either or a combination of both would make this go down. So remember that. Let's see, another question. Which of the following would cause the bulb to shine less brightly? Now, imagine I had a circuit, okay? Again, I keep talking about these circuits, but let me actually draw one out. So again, the positive end, I usually like to make a square. So remember, this is the positive end, and this is the negative end. And another analogy, just imagine you dropping something from a cliff with high potential down to the bottom with low potential. That is essentially what's happening here, but with a charge instead of a rock. Now, my next question is, a certain electrical circuit contains a battery with 3 cells. So I guess I could draw that like this. Each one of those representing a battery. And then if I have 3 cells and a light bulb, the question is asking me what would need to happen for the light bulb to shine less brightly. And this is actually the first question that I asked you. They're the same thing, just they're asking different things. The first one was asking which one would cause less current to flow, and this is asking what would cause the light bulb to shine less brightly. And they both mean the same thing. For this to shine less brightly means that there needs to be less current flowing through it. So for less current to be flowing through it, resistance needs to go up and voltage needs to go down. If the resistance of a circuit were tripled, then the current through the circuit would be, so let's think of it this way. let's assume V stays constant. So I just have some value. This doesn't change. But if I had some I and some resistance, now in this situation, if I had a new circuit with the same voltage, so this will stay the same, whatever number that is, the relationship between the current and the resistance needs to stay the same. So if I had some new resistance that was actually 3 times bigger than this one, my new current would have to have some ratio compared to this to equal this. So if this is 3 times bigger, what does this have to be for this to remain the same? So think of fractions. This should be 1/3 of the size. I have another question asking, if the voltage across a circuit is quadrupled, then the current through the circuit would be, So now let's look at this situation again. If the voltage is quadrupled, now did I say anything about the resistance? That should stay the same. So if this stays the same, and this is quadrupled, what should happen here? Well, that should be quadrupled as well because they are directly proportional. I asked you some other questions after that. So these are theoretical questions. Now let's get down to the nitty-gritty with actual calculations. In general, I always care about the idea more, but I need to make sure that you understand how to do these calculations. It's physics, of course. We use numbers. That's what we do. Now, my question is, if you have a circuit that has a power supply, a resistor, and an ammeter. An ammeter is something that measures amps, okay? So it measures current. The ammeter reads a current of, so I equals 24 milliamps. Determine the new current if the voltage of the power supply, so this is my original current, I'll call it I naught. So determine the new current if the voltage of the power supply was increased by a factor of 2. So if my old voltage was increased by a factor of 2, that means times 2, what is going to be my new current? I, if my resistance stays the same. So resistance naught equals my new resistance. So I need a numerical value here. So remember kind of how we mentioned this before. If my resistance is the same and I change my voltage, what's going to happen to my current? So if I multiply my voltage by 2 and my resistance stays the same, then my current is going to also be multiplied by 2. So my new current is going to be 2 times 24 milliamps, which will equal 48 milliamps. Nice. In the same situation with the same current, I naught being 24 milliamps. If I decreased my voltage by a factor of 2, so that means my voltage by 1/2, and the resistance was increased by a factor of 2. So my new resistance is times 2. So let's just plug that into this equation. So if I have 1/2 V equaling some new I, which I don't know, times 2R what happens to this current. So I will have to be, and I'm going to have to bring this 2R to the other side. This means I will have 1/2 delta V divided by 2R. And if you know your algebra well, that should actually be 1/4 of delta V over R. Now, remember in this situation, the initial current is actually delta V over R, which is 24 milliamps. So what I'm going to have to do is get 24 milliamps and just divide that by 4. You should be able to do this. So my new current is actually 6 milliamps. Now I like this question right here because it helps explain a few things. I will write it again. It says an electric device with the resistance of 3 ohms. So let us write this. Resistance 3 ohms will allow a current of 4 amps to flow through it. 4 amps to flow through it if a voltage drop of blank volts is impressed across the device. So this is what I'm trying to find, the voltage drop. Now this is important terminology. Okay, so let me draw a circuit for you. If I have some very small circuit, very simple circuit, which looks like this. So this of course is the battery or the power supply, and this little zigzag demonstrates that the path will be a little difficult for the charge to flow through, so it represents the resistor. Makes sense, right? Now there's this thing called voltage drop. So if I have some unknown potential difference here, so imagine like the height, okay? If I have some unknown potential difference here, then think of it being used up. So if I have an object that I drop from here to here, what's going to happen to the potential as it's at the bottom? The potential gets used up. Same thing happens in a circuit. So forget about this problem right now. If I have some voltage, let's just say I had 10 volts in this circuit. If I had 10 volts right here, voltage, potential difference, once I go through a resistor, that potential difference will have to be used up like a currency. It'll essentially, once it hits the resistor, it'll drop. It'll just, it'll start from here. Imagine right here, it'll be at the top, and once it gets through that resistor, this is its only obstacle, so it'll be right at the bottom. So whatever potential it did have at the very beginning going from here to here, it used up with this one resistor. So that's what we call a voltage drop. So whatever the voltage is here, if I have one resistor, the voltage drop through this one resistor will be the same as the voltage right here at the very beginning. Later on, we will get into more complex types of circuits, but for right now, if I have one resistor, whatever the voltage drop from here to here is through the resistor or across the resistor, it will equal the voltage at the beginning of the source, either the battery or something else. So the voltage drop here is going to be equal to the voltage from the beginning. So that's pretty important. Again, in this situation, the resistance of this resistor is 3 ohms and the current is 4 amps. This is quite simple. V equals IR. Not a very complex problem at all, but those ideas are quite important that I just pointed out. So 4 amps, I like parentheses, times 3 ohms. The voltage drop through this resistor is going to be 12 volts. Something else to take note is if I only have one wire right here, the current, imagine one road and you have many cars flowing on there. Whatever the rate, however many cars are on here are going to have to end up here. So there's only one way to go. Because there's only one way to go, that means the current is going to be the same everywhere. So if I refer to the current right here, or actually right here through this resistor as 4 amps, then the current actually right here after the battery will be the same. It will be 4 amps. And then the current right after the resistor, it will be 4 amps as well. Those are very important things to remember. And if I have only one resistor, whatever the resistance of this resistor is in this circuit, it will be the resistance of the whole circuit if there's only one resistor. So these are 3 important things to remember. The voltage drop through one resistor in this circuit will be equal to the voltage, the electric potential at the beginning. And then if there's only one resistor like this, there's only one path to go. Or if there's only one wire, there's only one path to go, so the current will be the same. Very important things that we'll need to know going forward. Have a great day. Peace.